All right, last video, and in here we're going to discuss kind of a couple interesting examples. Well, one interesting example, and then one's kind of like plain Jane. That's fine. So then vector field, okay, fine. All this stuff is normal. Okay, we have a fun parameterization, and if you end up graphing that parameterization in Wolfram Alpha, you get this sort of image. So think of it as like a tornado almost. It's a little bit wider in the middle than at the bottom, so it's not, conical exactly. But here we go, and we want to evaluate this, right? Well, this is kind of interesting because if I want to apply Gauss's theorem, and that's probably what you're thinking, like, okay, it's just another example of Gauss's theorem. We go through the conditions, right, and we're going to end up failing because we don't have a closed surface. There's no top. So what we're going to end up doing is adding in a disk on the very, very top of this. So if you can imagine covering this now with a disk, and we're going to call this disk at the top S prime. If we add that in together with the boundary of this tornado, then we should get something that is closed. Okay. All right. So then another thing that so then it certainly satisfies the conditions then of Gauss's theorem. Okay, after that, we would need to check that we have the normals in the right direction, and it does say we have upward, so this is going to be okay. All right, so then if we look at this thing a little closely, first thing that we can do is we know we're going to need to compute the divergence at some point. So if I go ahead and compute that now, well, this has no x, that has no y, and that has no z. So we dot it, and we're just going to get 0. So that's really interesting. If as soon as we check on our exam or whatever that we satisfy the conditions for Gauss's theorem, we can say, okay, well, the triple integral over d is, and then of the divergence, dv, is equal to the vector surface integral over the closed boundary of f dot ds. We know that this whole thing is 0. So then when we look at the vector surface integral over the closed boundary, this is going to be the let's see. So we're going to have this s f dot ds. I do need to fix this in just a moment. Okay, and then plus integral over s prime of f dot ds. Okay, so now I kind of skipped over one thing. So it said with upward pointing normals. Okay, so if it's pointing upwards, that is, in this figure, if you were to continue it for larger values of u and larger values of u, that is, it would actually look similar to that cylinder with its ends punched in. So just know that that's what it looks like. But upward pointing normals are actually pointing inward here, and we need outward. So what we need to do here is also add in a negative sign because this is pointing in the wrong direction. We need outward pointing normals. Okay, so then when we do that, what we end up getting, if we just rearrange this, if we want to look at, okay, so separating these things on different sides is equal to integral over s prime f dot ds. Okay, and so here we can technically we're done. We've evaluated by saying, oh look, it's equal to another double integral, and we could compute this second one a little bit more easily because it's just a disk, and we can parameterize the disk using polar coordinates and use that composition here and find ds in here, but I'm not going to go through that work because it's more work than it's worth for the concept level. The only reason that we were able to do this again is just that we recognize that since the divergence was 0, this whole side is 0. Otherwise, in other scenarios, you would need to compute that. Okay? All right. The last example, this is kind of the plain Jane one. Okay, so we have this vector field and we want to find the flux. Okay, so if we want to find the flux, let's see, and it is a solid thing. So if we want to find the flux, okay, over the boundary of f dot ds. Okay, well we can. And okay, so this is going to satisfy the conditions of Gauss's theorem. So we're going to say that this is the triple integral over d of the divergence dv. Okay, when we compute the divergence, we end up getting, okay, so divergence, let's see what that is. So this part here is going to be x squared plus y, and then that's going to be 0, and then we're going to get plus y squared minus y. Okay, so those are going to end up canceling, and we just get x squared plus y squared. Okay, so then this happens to be really nice if we recognize x squared plus y squared, where we can parameterize that using polar. So let's use x as r cosine theta, and y is r sine theta. Sorry, not polar, cylindrical. So then we're going to have this triple integral. Okay, we're going to have, and then this is just r squared, and then, I don't know, let's pick dr, d theta, dz. Okay, r is going to go, okay, so this is just going to go from 0 to 1 because of that condition, and then theta is going to go from 0 to 2 pi, and then z is going to go from 0 to 2. Okay, and so then we can do all this, and we just end up with, after computing or sticking interval from alpha, we get pi. Yay! We ended off this semester with a nice example with pi. Okay, so just another example of how you can use Gauss's theorem, and that'll conclude this video and all the videos for Calculus 3. Congratulations to making it to the end of the semester.